In linear algebra, an n by n square matrix A is called invertible if there exists an n by n square matrix B such that wherein denotes the n by n identity matrix and the multiplication used is ordinary matrix multiplication. If this is the case, then the matrix B is uniquely determined by A and is called the inverse of A, denoted by or1. A square matrix that is not invertible is called singular or degenerate. A square matrix is singular if and only if its determinant is 0. Singular matrices are rare in the sense that a square matrix randomly selected from a continuous uniform distribution on its entries will almost never be singular. Non-square matrices do not have an inverse. However, in some cases such a matrix may have a left inverse or right inverse. If A is m by n and the rank of A is equal to n, then A has a left inverse, an n by m matrix B such that BA equals I. If A has rank m, then it has a right inverse, an n by m matrix B such that AB equals I. Matrix inversion is the process of finding the matrix B that satisfies the prior equation for a given invertible matrix A. While the most common case is that of matrices over the real or complex numbers, all these definitions can be given for matrices over any commutative ring. However, in this case the condition for a square matrix to be invertible is that its determinant is invertible in the ring, which in general is a much stricter requirement than being non-zero. The conditions for existence of left inverse resp. right inverse are more complicated since a notion of rank does not exist over rings. Properties: the invertible matrix theorem, let A be a square n by n matrix over a field K. The following statements are equivalent, that is, for any given matrix they are either all true or all false. A is invertible, that is, A has an inverse, is nonsingular, or is nondegenerate. A is row equivalent to the n by n identity matrix in. A is column equivalent to the n by n identity matrix in. A has n pivot positions. Det AA permel 0. In general, a square matrix over a commutative ring is invertible if and only if its determinant is a unit in that ring. A has full rank. That is, rank A equals n. The equation arcs A equals A0 has only the trivial solutions A equals A0, null A equals 0. The equation X equals B has exactly one solution for each B and Kn. The columns of A are linearly independent. The columns of A span Kn, kernel A equals Kn, the columns of A form a basis of Kn. The linear transformation mapping X to X is a bijection from Kn to Kn. There is an n by n matrix B such that AB equals n equals BA. The transpose AT is an invertible matrix. The number 0 is not an eigenvalue of A. The matrix A can be expressed as a finite product of elementary matrices. The matrix A has a left inverse or a right inverse, in which case both left and right inverses exist and B equals C equals A1. Other properties: furthermore, the following properties hold for an invertible matrix A, or 1, A1 equals A. Kiloampere, A1 equals Car1 or 1 for non-zero scalar K. AT, A1 equals T. For any invertible n by n matrices A and B, A1 equals bar1 or 1. More generally, if A1 arc are invertible n by n matrices, then A1 equals also known as 1 or 1A2 or 1A1 or 1. Det, or 1, equals det, A1. A matrix that is its own inverse, that is, A equals or 1 and A2 equals I, is called an involution. In relation to the identity matrix, it follows from the theory of matrices that if for finite square matrices A and B, then also density, over the field of real numbers, the set of singular n by n matrices, considered as a subset of a n, n, is a null set, that is, has Lebesgue measure 0. This is true because singular matrices are the roots of the polynomial function in the entries of the matrix given by the determinant. Thus in the language of measure theory, almost all n by n matrices are invertible. Furthermore, the n by n invertible matrices are a dense open set in the topological space of all n by n matrices. Equivalently, the the set of singular matrices is closed or nowhere dense in the space of n by n matrices. In practice, however, one may encounter non-invertible matrices. And in numerical calculations, matrices which are invertible, but close to a non-invertible matrix, can still be problematic. Such matrices are said to be ill-conditioned. Methods of matrix inversion. Gaussian elimination. Gauss-Jordan elimination is an algorithm that can be used to determine whether a given matrix is invertible and to find the inverse. An alternative is the LU decomposition, which generates upper and lower triangular matrices which are easier to invert. Newton's method. A generalization of Newton's method as used for a multiplicative inverse algorithm may be convenient, if it is convenient to find a suitable starting seed. Victor Pan and John Rafe have done work that includes ways of generating a starting seed. Byte magazine summarized one of their approaches as follows: the Pan-Rafe breakthrough consists of the discovery of a simple and reliable way of evaluating BO, the initial approximation to A1, which can safely be used for starting Newton's iteration or variants of it. Readers interested in a derivation can consult the references. I give here merely one example of the results. Let me denote the Hermitian transpose of A by AH. That is, if A, I, J, is the element in the ith row and JTH column of the A matrix, then A, J, I, is the element at the corresponding position in the matrix A. Here the star denotes complex conjugate. If, as is the case to which I have limited all my own calculations, the elements of A are all real, then AH is just the transposed matrix AT of A. We now introduce a number T, defined by equation 8. In words, we consider the magnitudes of the various elements A, I, J, of the given A matrix that is to be inverted. We add up the magnitudes of the elements in a given row and records the sum. We do the same for the remaining rows and then compare the sums thus obtained. The largest of these row sums, just a number, is designated. We do the same for the column sums and take the product of these two maxima, designating its reciprocal as the real number T. Finally, we define our initial approximate inverse matrix BO as shown in equation 9. That is, the number T multiplies every element of the Hermitian transpose of the A matrix. Pan and Rafe give alternative forms, but this will do. And that's all there is to it. Otherwise, the method may be adapted to use the starting seed from a trivial starting case by using a homotopy to walk in small steps from that to the matrix needed, dragging the inverses with them, wherein for some terminating n, perhaps followed by another few iterations at A to settle the inverse. Using this simplistically on real-valued matrices would lead the homotopy through a degenerate matrix about half the time, so complex-valued matrices should be used to bypass that, for example by using a starting seed S that has I in the first entry, 1 on the rest of the leading diagonal, and 0 elsewhere. If complex arithmetic is not directly available, it may be emulated at a small cost in computer memory by replacing each complex matrix element A plus B with a 2A, 2 real-valued submatrix of the form. Newton's method is particularly useful when dealing with families of related matrices that behave enough like the sequence manufactured for the homotopy above. Sometimes a good starting point for refining an approximation for the new inverse can be the already obtained inverse of a previous matrix that nearly matches the current matrix, for example the pair of sequences of inverse matrices used in obtaining matrix square roots by Dem and Beaver's iteration. This may need more than one pass of the iteration at each new matrix, if they are not close enough together for just one to be enough. Newton's method is also useful for touch-up corrections to the Gauss-Jordan algorithm which has been contaminated by small errors due to imperfect computer arithmetic. Kelskiy-Hamilton method. Kelskiy-Hamilton theorem allows to represent the inverse of A in terms of det, A, traces and powers of A. Where n is dimension of A, and the sum is taken over S into sets of all K L % 0 yen satisfying the linear Diophantine equation. E again decomposition. If matrix A can be E again decomposed and if none of its eigenvalues are 0, then A is nonsingular and its inverse is given by where Q is the square matrix whose ith column is the eigenvector of A and I is the diagonal matrix whose diagonal elements are the corresponding eigenvalues, that is. Furthermore, because I is a diagonal matrix, its inverse is easy to calculate. Kelskiy decomposition. If matrix A is positive definite, then its inverse can be obtained as where L is the lower triangular Kelskiy decomposition of A, and L denotes the conjugate transpose of L, analytic solution. Writing the transpose of the matrix of cofactors, known as an adjugate matrix, can also be an efficient way to calculate the inverse of small matrices, but this recursive method is inefficient for large matrices. To determine the inverse, we calculate a matrix of cofactors. So that where A is the determinant of A, C is the matrix of cofactors, and CT represents the matrix transpose. Inversion of 2A, two matrices. The cofactor equation listed above yields the following result for 2A, two matrices. Inversion of these matrices can be done easily as follows. This is possible because 1/add BC is the reciprocal of the determinant of the matrix in question, and the same strategy could be used for other matrix sizes. The Kelskiy-Hamilton method gives inversion of 3A, three matrices. A computationally efficient 3x3 matrix inversion is given by where the determinant of A can be computed by applying the rule of Saris as follows. If the determinant is non-zero, the matrix is invertible, with the elements of the above matrix on the right side given by the Kelskiy-Hamilton decomposition gives the general 3A, 3 inverse can be expressed concisely in terms of the cross product and triple product. If a matrix is invertible, its inverse is given by note that is equal to the triple product of, and the volume of the parallelepiped formed by the rows or columns. The correctness of the formula can be checked by using cross and triple product properties and by noting that for groups, left and right inverses always coincide. Intuitively, because of the cross products, each row of is orthogonal to the non-corresponding two columns of. Dividing by causes the diagonal elements of to be unity. For example, the first diagonal is inversion of 4A, 4 matrices, with increasing dimension, expressions for the inverse of A get complicated. For n equals 4 the Kelskiy-Hamilton method leads to an expression that is still tractable. Blockwise inversion, matrices can also be inverted blockwise by using the following analytic inversion formula, where A, B, C and D are matrix subblocks of arbitrary size. This strategy is particularly advantageous if A is diagonal and R(1)B is a small matrix, since they are the only matrices requiring inversion. This technique was reinvented several times and is due to Hans Buls, who used it for the inversion of geodetic matrices, and to Tadeusz Banachkiewicz, who generalized it and proved its correctness. The Nullity Theorem says that the nullity of A equals the nullity of the subblock in the lower right of the inverse matrix, and that the nullity of B equals the nullity of the subblock in the upper right of the inverse matrix. The inversion procedure that led to equation performed matrix block operations that operated on C and D first. Instead, if A and B are operated on first, and provided D and or BDA1C are nonsingular, the result is equating equations and leads to where equation is the matrix inversion lemma, which is equivalent to the binomial inverse theorem. Since a blockwise inversion of a now, n matrix requires inversion of 2 half-sized matrices and 6 multiplications between 2 half-sized matrices, it can be shown that a divide-and-conquer algorithm that uses blockwise inversion to invert a matrix runs with the same time complexity as the matrix multiplication algorithm that is used internally. There exist matrix multiplication algorithms with a complexity of O, n 2.3727 operations, while the best proven lower bound is I copyright, n2 log n. By Newman series, if a matrix A has the property that then A is nonsingular and its inverse may be expressed by a Newman series. Truncating the sum results in an approximate inverse which may be useful as a preconditioner. Note that a truncated series can be accelerated exponentially by noting that the Newman series is a geometric sum. Therefore, if one wishes to compute terms, one merely need the moments which can be found through L matrix multiplications. Then another L matrix multiplications are needed to obtain the final result by multiplying all the moments together. Therefore, two L matrix multiplications are needed to compute terms of the sum. More generally, if A is near the invertible matrix X in the sense that then A is nonsingular and its inverses. If it is also the case that AX has rank 1, then this simplifies to derivative of the matrix inverse. Suppose that the invertible matrix A depends on a parameter T. Then the derivative of the inverse of A with respect to T is given by. To derive the above expression for the derivative of the inverse of A, one can differentiate the definition of the matrix inverse and then solve for the inverse of A. Subtracting from both sides of the above and multiplying on the right by gives the correct expression for the derivative of the inverse. Similarly, if is a small number, then Maria Penrose pseudo inverse. Some of the properties of inverse matrices are shared by Maria Penrose pseudo inverses, which can be defined for any m by n matrix. Applications. For most practical applications, it is not necessary to invert a matrix to solve a system of linear equations. However, for a unique solution, it is necessary that the matrix involved be invertible. Decomposition techniques like LU decomposition are much faster than inversion, and various fast algorithms for special classes of linear systems have also been developed. Matrix inverses in real-time simulations. Matrix inversion plays a significant role in computer graphics, particularly in 3D graphics rendering and 3D simulations. Examples include screen-to-world raycasting, world-to-subspace-to-world object transformations, and physical simulations. Matrix inverses in MIMO wireless communication. Matrix inversion also play a significant role in the MIMO technology in wireless communications. The MIMO system consists of N-transmit and N-receive antennas. Unique signals, occupying the same frequency band, are sent via N-transmit antennas and are received via N-receive antennas. The signal arriving at each receive antenna will be a linear combination of the N-transmitted signals, forming a NXM transmission matrix H. It is crucial for the matrix H to be invertible for the receiver to be able to figure out the transmitted information. See also, binomial inverse theorem, LU decomposition, matrix decomposition, matrix square root, Maria Penrose pseudo-inverse, singular value decomposition, Woodbury matrix identity, notes. References: Corman, Thomas H. Lesserson, Charles E., Revist, Ronald L., Stein, Clifford, 1990. 28.4 Inverting Matrices. Introduction to Algorithms. MIT Press and McGraw-Hill pp. A pp. 755 a €760. ISBN A0-262-03293-7 External links, Haswinkel, Mikhail, ed., Inversion of a Matrix, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4 Matrix Mathematics, Theory, Facts, and Formulas at Google Books, Equations Solver Online, Lecture on Inverse Matrices by Khan Academy, Linear Algebra Lecture on Inverse Matrices by MIT. LAPAC is a collection of Fortran subroutines for solving dense linear algebra problems. Alglib includes a partial port of the LAPAC to C++, C, Delphi, etc. Online inverse matrix calculator using Ajax, symbolic inverse of matrix calculator with steps shown, more Penrose pseudo-inverse, inverse of a matrix notes, module for the matrix inverse, calculator for singular or non-square matrix inverse, the matrix cookbook, derivative of inverse matrix at planetmath.org.